In the video, I want to talk about simple harmonic motion. And simple harmonic motion is that simple, and it means simple, and I'm going to talk about that in just a minute, but it's that simple back and forth motion. So if we have an object and it just simply vibrates and it just simply goes back and forth, then that is called simple harmonic motion. Now the reason we want it simple is because we want small angles, or we want small displacement, and that makes it simple. I'm going to talk a little bit more about that when we talk about the pendulum. But let's say I have a rope, and so let's just pretend this is a rope, and I look at one small little part of the rope, and what I'm going to do in this rope is I'm going to send a pulse through it. So in other words, I'm going to shake the rope up and down one time, and so what's going to happen is it's going to send a pulse through, and this will propagate through the rope till it gets over here to the end. Well, what's taking place with the medium? Well, if I just take a little cross section of this and I have the medium of the rope, then what's going to happen when that pulse hits? Now remember, this pulse has a certain amount of energy to it. And so when the energy hits here, then each one of these is going to vibrate up or down based upon the motion of the wave. And this vibration, this energy, is transferred throughout from one to the next until we go all the way through this rope. And that's going to give me that simple back and forth motion that we're looking for, which is what a wave is. So how does that translate to a pendulum? A pendulum, we've got the different parts, and so this is called a bob, and then of course we have the string. So let's put the string. And so the bob is just simply going to go back and forth. So if I displace it here, then this is going to swing back and forth in our simple harmonic motion, just back and forth, back and forth. Now what I want are small angles, so the angle between here and there needs to be small, and so let's give it a number. Let's say that angle has to be equal to or less than 13 degrees. And the reason is if we go a larger angle, it's like swinging on a swing set. If you wanted to go higher, you had to use more force. That's no longer simple. So we just want simple harmonic motion. We just want that simple back and forth motion that takes place. So as the pendulum, as we displace it here, the pendulum is going to swing. Now that gives us a couple different things. First of all, how much do I displace? Well, remember, if I take it right through the center of this object, so if I take it right through the center here, then the displacement is not along the arc. The displacement is how far it is from here to here. This is my displacement. Now, this arc swing, once I displace it here, it's now going to gain velocity as I let go. And it's going to swing to the left, and then when it reaches here, it's going to stop and then come back this way. So it's that back and forth motion that a pendulum has. We can calculate the velocity using our potential and kinetic energy. So 1/2 mass velocity squared is equal to our mass times gravity times height. And so our height, remember, is this right here. How high do I displace it? Now it's a little bit more complicated than that when you start taking into account the length and the change in the length and the different factors that are involved. But we can use this right here to calculate our velocity of this pendulum. Now, a couple of things. Time period. Now remember, time period is equal to 1 divided by the frequency. But we can calculate the time period of a pendulum in a different way. If I have the length, I can say my time period, if I have the length and I have gravity, so this time period, this back and forth motion, now remember, we're going to start here and we're going to stop here. So back and forth one time is my time period. How long does it take to go back and forth one time? And so since that is part of a circle, it's 2 pi, and then I'm going to do the square root of the length of the string divided by gravity. That formula will give me the time period of a pendulum. That tells me a few things, but the most important thing that it tells me is that the period of a pendulum is independent to the mass. Doesn't make any difference what the pendulum is. The only thing that affects the time period is going to be the length of the string. The amplitude, it is independent to amplitude. Now once again, we're still talking simple harmonic motion, and we're going to talk about forces and all that kind of stuff, but if you're simple harmonic motion, we're small angles. So in that case, the only thing that comes into the equation for the time period of a pendulum is going to be the length of the string. And so if we look at this animation is showing me what's happening to the velocity and acceleration. So notice when the object is right here, the acceleration is 0. The acceleration is pointing straight up. So right here, let me go ahead and put my formula. Time period is equal to 2 pi times the square root of length divided by the gravity. And once again, that's the time it takes for it to go back and forth one time. So what about Hooke's law? Hooke's law tells me that the force and the displacement of a spring are proportional to each other. So that means this. That means that let's add a mass. Well, I have a spring, and it's just hanging to a certain level. It's just at rest. And then I'm going to take a mass and I'm going to hook it to it. So let me hook that together. So now what I have is I have this object that's hanging, and it's hanging at rest. So we're going to call this line my equilibrium line, because this is where it will be at rest. So I'm going to put over here equilibrium. That's an IUM. All right, so let me get this out of the way. Let's move it over here. So now with Hooke's law, what that means is that what happens if I decide to displace this. So now let's say I stretch this down, and I'm going to stretch it down to a certain place. Well, once again, just like I did with the pendulum, the distance of displacement is the distance from here to here. Now, Hooke's law tells me that the more force that I apply here, the more displacement I'm going to have. Hooke's law, my formula is force is equal to a negative K times X. K is my spring constant. But notice in the formula that it is negative. And that's because the force is always going opposite of the direction of motion. So if this is being pulled down, the force of the spring is pulling against it. Same thing if I take this and I let go, and this just simply goes up to here, and now I have an equal displacement on top of this. Then what happens is the spring is now pushing down as this goes up, and so now this is going to just simply bob up and down. That is once again my simple harmonic motion, and you can see that it starts here, it's going to come down, and then it's going to go up, and this action will just simply continue as this spring bobs up and down. So if I put this into time and space, I get my sine curve from Hooke's law. And so the bob of the motion of this bob moving up and down on the spring gives me my simple harmonic motion. And I can calculate. My x is my displacement, so that's going to be the distance between the lines, and then of course the force is the mass times gravity of whatever my object happens to be. My time period for a spring is very similar to the time period for a pendulum. My time period, once again, is 2 pi. Now, it's 2 pi because if you remember, we're still going around our circle, so to speak. So from here to here would be 2 pi. In any two consecutive points. So from here, let me change colors. So from here to here would be 2 pi. From here to here would be 2 pi. That's one wavelength, that's one time period. So 2 pi times the square root, but instead of length, I don't have length, I have mass. So the mass divided by the spring constant will give me the time period of a spring. So hopefully we have a better understanding of what simple harmonic motion is, and as it applies to both a pendulum and a spring.